Hey guys, welcome to Geometry. This is Mr. O'Shea. Today we're going to be talking about kind of furthering our discussion from Pythagorean theorem and right triangles. We're going to specifically talk about special right triangles today. We're going to focus on two of them. So today's topic is about special right triangles, the focus being that they are still right triangles. So we're talking about two, and we're talking about 45, 45, 90 right triangles, and the other one's going to be 30, 60, 90 right triangles. 45, 45, and 90, that adds up to 180, and 30, 60, 90 also adds up to 180. So what you guys should hopefully realize, kind of make that connection there, is that when we talk about 45, 45, 90, we're actually talking about the angle measurements of the triangle. And then 30, 60, 90, we're also talking about the angle measurements of the triangle. So we're talking about two very distinct right triangles that have other specified measurements. So let's go ahead and look at the 45, 45, 90 examples. Let's go ahead and draw out a 45, 45, 90 right triangle. So there's our right triangle, and it's going to have two congruent angles. Essentially, we want a right isosceles triangle. We know it's isosceles because the two angles are congruent. So we can call those two congruent sides, what if we call those x and x? Trying to find the third side. And because it's a right triangle, we can still use Pythagorean theorem and say a squared plus b squared equals c squared based off the idea it's 90 degrees, but we want to know what is that c, right? We know the other two have to be x because 45, 45, 90, those two angles are both going to be 45 degrees, which means those two sides are congruent, but what is that third side? We're going to use Pythagorean theorem to actually go ahead and figure this out. So we can say Pythagorean theorem is a squared plus b squared equals c squared. But we're going to substitute our values in. We're going to say x squared plus x squared, because that is a, and b was really x as well. So x squared plus x squared. We don't know what c is, so we'll call it c for right now, because that's what we're actually solving for. So x squared plus x squared, that's going to be 2x squared. And to get rid of that c, to figure out what c is, we could take the square root of it. If we take the square root of the other side, that's really the square root of 2 and the square root of x squared. And we can kind of break the 2x squared into two different pieces. Similarly, kind of how when we reduce radicals, we break the numbers up. 2 times x squared, we can just write it as the square root of 2 times the square root of x squared, and we'll see why in just a minute. Let's keep going here. And the square root of c squared, we should know that square roots and squares, they kind of cancel each other out. So the square root of c squared just turns into just regular old c. And that same thing is going to happen with x, same principle there. But square root of 2, we can't reduce it all, so that's going to be the root 2. And that'll just turn into x. So c equals root 2 times x. Now we're going to rewrite this slightly different. I'm going to take the position of root 2 and take the position of x, and I'm just going to flip them, because in multiplication we can flip things and it doesn't really matter. It doesn't change anything. So what we see is that the answer is that c equals x times root 2. And that's going to be our pattern that always exists. In a 45, 45, 90 right triangle, it's always going to go x, x, and then your hypotenuse is going to be your leg, x, times a factor of root 2. So it'll be x, x, x root 2. We'll do an example with a couple of numbers, and you guys can see what I mean by this. So if we took a triangle, and it was a right isosceles triangle, so we'll draw out the right triangle, and we'll make it isosceles, just meaning that the two angles are congruent. So we know it's going to be a 45, 45, 90 right triangle. And I'll give you one side length. We'll say that this side over here is 3. Find the other two sides. Well, the first one, the easy one, is the fact that it's isosceles. Those are both congruent angles, so those sides are congruent. So we know it's 3. We can find the hypotenuse using a squared, b squared, and c squared. We could use the Pythagorean theorem. And you guys could go through the work to show that a squared plus b squared equals c squared and start plugging in our numbers that we have. So really 3 squared plus 3 squared equals c squared. And the math on that would be 9 and 9, which is really 18, equals c squared. And we will go ahead and take the square root of both sides. And square root of 18 is a decimal, so we're going to break it up, try to reduce it. I see that could be 9 and 2, so it's really root 9 times root 2. Right? 9 is a perfect square, that's just 3, and root 2. Awesome. So that's what c is, 3 times root 2. So c is 3 root 2. Now, what we should realize is that we didn't actually have to do all this math, all of those calculations, the whole Pythagorean theorem. We didn't need it on this one. If we recognize that pattern of 45, 45, 90, special right triangle, always being x, x, x root 2, or leg, leg, leg root 2. So your two legs were x and x, in this case 3, and your hypotenuse is x root 2, so 3 root 2. That'll always be true, by the way, every single time we have a 45, 45, 90. So now let's transition into the 30, 60, 90s. 30, 60, 90. Now to go about this and kind of prove it, we're going to look at it slightly different. We're not going to draw 30, 60, 90 right away. We're going to draw a big equilateral triangle where every single side length is the same, which means every angle measurement is also the same. All your side lengths, we'll call those x. You know, let's use some numbers. Let's not use x on this. I think it'll be a little difficult to comprehend if we use x. We'll use a number. We'll use 6. So each side length is 6, and each angle measurement is going to be 60 degrees because it's an equilateral triangle. But I don't want the equilateral triangle, I want a 30, 60, 90 right triangle. So what we're going to do here is we're going to take this and we're going to draw an altitude down from the top of the vertex. Right? And that's when I created my 30, 60, 90 right triangle. So really I didn't need all that stuff. I'll get rid of it, I'll clean it up a little bit. And I know you guys don't have the luxury of doing that on your papers, but we're going to get to the same idea here. I just want to show you guys where this all stems from. Now if you had the other side of the triangle, what we realized is that the top was 60 and I cut it in half, so it's really 30 degrees. And there's my altitude, so that's how I developed that 30, 60, 90 idea. That full bottom, the full bottom's 6. So that means that that side over there is really going to be half of that, which is 3, right? Because I cut it in half and half. So on a 30, 60, 90 right triangle, so far I've got two measurements. What is the distance of the altitude? How big is that? And we could use Pythagorean theorem and solve that out, right? A squared plus b squared equals c squared. And your a and b, well, that's going to be 3 and we don't know, so 3 squared plus, we'll leave b squared equals c squared, which is 6. 3 squared is 9. We don't know a b, and that's going to give us 36. So we will subtract 9 from both sides to get b squared equals 27. We will then take the square root of both sides and break 27 up because that's a decimal. 27 could really be 9 times 3. And 9 is a perfect square, so we're left with 3 times root 3 is our final answer. So the altitude on this was 3 root 3. Now that was a lot. I didn't want to confuse you guys with the x's, but I do want you guys to realize what those numbers are. 3, 3 root 3, and 6. Those have a relationship, and I think that given time you guys can figure that relationship out, but I'm just going to go ahead and give it to you anyways. If we had the 30, 60, 90 right triangles, they always follow that pattern. 3, 3 root 3, and 6, but obviously the numbers could change if the 6 changed, or so on and so forth. So what we're going to do is we're just going to draw a 30, 60, 90 right triangle. We're just going to jump straight to the 30, 60, 90. We're not going to draw an equilateral and cut it in half or anything. We'll say here's my 60 and my 30's up on top. Across from your 30-degree angle, let's go across from the 30. We'll call that one x, okay? So in the top part, across from the 30-degree angle is 3, so we'll call that one x anytime we're across from the 30, the angle opposite the 30 degrees, that's going to be our x. Now the angle opposite your 60 degrees is going to be x times a factor of root 3. And the one across from your 90 is going to be 2x. That's always going to work. And if you guys kind of go back and look at that again, we had 3, 3 root 3, and 6. So it still followed that same exact pattern. We could have picked any numbers and it still would have been the same thing. So we'll do a quick example here. Let's go ahead and draw out a triangle. It's going to be a right triangle. And this one's going to be a 30, 60, 90 right triangle. And we'll put the 30 degrees up here. 60 down here. I'm going to tell you guys, I'll give you one measurement. This side right here, that's 5 inches, or 5. Find the other two. Let's write that 5 a little nicer. All right. Now you guys could go back to this idea, well, 30, 60, 90, that really stems from the equilateral triangle, and that 5 would be half of the full thing, so that big long distance is 10, which means that's 10, right? You could go that way. But I'm going to push you guys away from that. I don't want you guys to think of it like that. I want you guys to think of it in the terms of the special right triangle we just developed. So let's get rid of this. We said that these 30, 60, 90s always follow a pattern. Across from your 30 is going to be x. Across from your 60 is always going to be x times a factor of root 3. And across from your 90 is going to be twice the distance of x. So if x was 5, like we have there, that side is going to be 2 times 5, or just 10, which is what we found when we made that equilateral triangle, right? And the top is going to be x times root 3, or 5 times root 3. And if you guys did the Pythagorean theorem on that one, you guys would have got 5 root 3 as well. So to recap, we got two main ideas here that are going to make our lives a lot easier when we're dealing with right triangles. If you have an isosceles right triangle, which means it's a 45, 45, 90 right triangle, the side measurements are always going to follow this ratio. X, x, and your hypotenuse is going to be the leg times a factor of root 2. If you have a 30, 60, 90 right triangle, we'll put the 30 down there this time. 30, 60, 90. Across from your 30, opposite from your 30, is always going to be your x. That's your short side. Across from your 60 is going to be that times a factor of root 3. And across from your 90 is going to be twice the length of x. If you guys can memorize this, it's going to benefit you guys quite a bit when we're moving forward in geometry. All right, I'll see you guys all tomorrow.